Hi, everyone, and welcome to Module 9, Lesson 1, where we're going to begin our conversation on thermochemistry and thermodynamics. Thermo, the word thermo prefix has to do with heat energy. So we're going to talk about that, talk about different calculations that can go along with this. So first off, energy is the capacity to do work or produce heat. Heat, which is symbolized with a lowercase q, you'll see me often writing it as a cursive q, like that, is energy that is transferred from one object to another due to a temperature difference. Heat is measured in joules or calories. Temperature is not the same as heat. Temperature is proportional to the average kinetic energy, which we talked about in the gas law module. So an intensive property, it doesn't matter the amount involved. An extensive property relies upon the mass or volume of matter. So temperature is intensive. It does not matter how much I have. If I've got 100 grams or 50 grams, it's still going to be the same temperature. An extensive property where it does rely upon the mass and specific heat, which is a new concept for us, is an extensive property because it does rely upon how much there is. So what is specific heat? Specific heat, which is AC as its symbol, is the quantity of heat needed to raise 1 gram of water by 1 degree Celsius. And we can calculate C. It's in terms of joules over grams times degrees Celsius. So to calculate C, it's heat, Q, divided by the mass times the change in temperature. Whenever you see a change in temperature, please note it's always the final temperature minus the initial temperature. So we're going to see that a lot in this module. So it's always final minus initial. Now, everything has a specific heat, all right? Everything has their own unique specific heat depending on the way the molecule is and its different properties. Metals have low specific heats because we know it doesn't take much energy to heat them up. Whereas water, for such a tiny molecule, water has a very high specific heat. It's 4.184 joules over grams degrees Celsius. So this is going to come up a lot. It's not anything that you need to remember, but it will come up a lot, and that's going to be a very important specific heat that we see. Now, I do have a video linked below in the resources for a demonstration that's pretty interesting. So you should go ahead and watch that video. Pretty interesting. The guy, I think his name is Steve Spangler. He has lots of interesting video demos for you if you're interested. So let's calculate heat transfer. Calculating heat transfer is the MCAT equation, Q equals MC delta T, where Q is heat in joules, M is mass in grams, C is the specific heat from before, and delta T is change in temperature. And we can use degrees Celsius here. So we're not going to Kelvin. Remember Kelvin, gas laws only. So let's use it here. Calculate the heat in joules needed to warm 10 milliliters of water from 0 degrees Celsius to 37 degrees Celsius. The density of water is 1 gram per milliliter. Great. So if I have 10 milliliters, I have 10 grams. That's what it's just saying to me. So I can just plug in my information. Q equals 10.0 grams times the 4.184 joules over grams degrees Celsius times, well, it's 37 minus 0, but you get the idea. And that gives me, with sig figs, 1550 joules. Okay. 3 sig figs, should be 2 sig figs, but we'll keep it with 3 from the temperature. So what would be the heat in kilojoules? Well, we just take those 1550 joules and say, okay, I know that 1 kilojoule is 1,000 joules. And that gives me 1.55 kilojoules. Kilojoules is more common when we're doing this. So don't forget how to do that conversion. It's pretty simple. Okay, so that's Q, which is heat. Now, enthalpy is the measure of heat content at a constant pressure. We are at a constant pressure within the room, so we can always use this term. So for us, Q and delta H is interchangeable. Delta H, change in enthalpy. We can think about it, change in heat. Same difference, same equation. Delta H equals MC delta T. Super important that we understand what our signs are telling us. Okay, so if it's a delta H is positive, it's endothermic. That means energy is going into it. If delta H is negative, it's exothermic, energy is coming out. That idea, if you don't understand that idea, this whole module is going to be terrible for you, okay? The idea of knowing that sign is super, super, super important. So make sure you understand the difference between a positive delta H and a negative delta H. So that's enthalpy. There are very many different types of enthalpy, and they all mean something different. So I'm just going to read through these, explain about them a little bit. You just have to be familiar with them. So the most common one is the enthalpy of reaction. So you see delta H and sub Rxn is the heat that is absorbed or released during a reaction. That's just general delta H. Enthalpy of combustion is the heat that's released when 1 mole is burned. Enthalpy of formation is the heat that's either absorbed or released when 1 mole is produced from its elements. So the formation is specific. It's forming a compound from its elements. Enthalpy of neutralization is the heat that's absorbed or released as 1 mole of an acid or base is neutralized. Enthalpy of vaporization is the quantity of heat absorbed in order to vaporize 1 gram of a liquid, typically in joules per gram, could also be in joules per mole or kilojoules per mole. It's interchangeable, you can change them. Enthalpy of fusion, this is the only one that's different. Fusion means melt, okay? So fusion is melting, the quantity of heat absorbed to melt 1 gram of a solid. So let's calculate heat that is due to a phase change. Heat is transferred when there's a difference in temperature, as we saw in the previous equation. But we also take into consideration the heat when we are going through a phase change. So molar heat of fusion is the energy required to melt 1 mole of a solid. This is the molar heat of fusion for water. It's a common one. Make sure you write that down and have it in front of you. The molar heat of vaporization is the energy required to vaporize 1 mole of a liquid. And then here is the delta H of vaporization for water. What would the molar heat of freezing and the molar heat of condensation be? Well, it's the same amount. So the whole idea with changing your state is we know that water melts at 0 degrees Celsius. We know that water freezes at 0 degrees Celsius. If that's true, how can it happen at the same temperature? It depends on where the heat's going. Is it going in or is it coming out? That's a super important concept with this too. If energy is going into it, it's melting. If it's coming out, it's freezing. So these molar heat of freezing, the delta H of freezing is going to be negative 6.02 kilojoules per mole. Okay, it's going to be the same amount, just the opposite sign. It needs to be released in order to freeze. Same thing, in order to condense, it needs to release 40.6 kilojoules per mole of energy. So that would be negative 40.6 kilojoules for condensation. And that's super important, understanding the idea that is the energy coming in or is it going out? And we can calculate the energy or the heat from a phase change. Q equals N delta H of the phase change, where N is the number of moles, as long as delta H is in terms of kilojoules per mole. Remember, it could be joules per gram. So you just have to pay attention to your units and make sure your units match. You just have to pay attention. That's super simple. So we want to calculate the heat needed to change 100 grams of water at 100 degrees Celsius into steam. If I'm turning it into steam, I'm going to be using the delta H of vaporization, which I know is 40.6 kilojoules per mole. So I need to take these 100 grams, I'll put 0.0 so I have more sig figs, and turn them into moles. I know that 1 mole of water is 18.01 grams, and that gives me 5.556 moles of H2O. And then once I have the number of moles, all I have to do is multiply it by 40.6. 5.556 times 40.6 gives me, I did my 6 different in this paper, 225.6 kilojoules. So that's how much energy is needed to change 100 grams of water into steam. So that's a lot of energy, really. And so one of the reasons why it takes so much energy and so much time to boil water, it takes a lot of energy in order to do that. And again, we know that that's true because of their intermolecular forces. Remember, throwback, intermolecular forces are involved when you're trying to change the state. So going from a liquid to a gas, vaporizing, needs to break those hydrogen bonds and therefore takes a lot of energy, as you can see. So, excuse me, we can look at a heating curve. It just is showing what happens over time to the temperature of your substance. So we know the freezing point is the temperature in which liquid is converted into a solid. The melting point is the temperature in which a solid is converted into a liquid. Again, these happen at the same temperature, which for water, 0 degrees Celsius. The boiling point, condensation point at the same temperature, which we know to be 100 degrees Celsius. It's just is the energy going in order for it to melt or boil, or is it coming out in order for it to freeze or condense? Boiling point we know is the temperature in which vapor pressure is equal to atmospheric pressure. Condensation point, the temperature in which the vapor has lost enough energy in order to turn into a liquid. Super important with these heating curves. Temperature remains constant during a phase change. So what happens? How do we get a heating curve for water? Take a big old beaker, jam pack it full of ice, put a temperature probe into it, put it on a hot plate. Turn the hot plate on, measure the temperature change over time. That's it. So what we do is from A to B, we're going to have a solid. That's what occurs from A to B. Okay, temperature probe in, heat it up, a solid. Until it has enough energy, until it gets to point B. Point B is going to be the melting point. Okay, and I'm increasing the temperature. I'm going this way, which is going to be an increase in temperature. Once it starts to melt, you have both a solid and a liquid. That flat line right there is the phase change. The temperature does not increase during the phase change until it has enough energy, and then it's nothing but a liquid. And then once it's a liquid, its temperature can start to increase again until you get to right here, which would be the boiling point. And now you're going to have a liquid and a gas. Again, the temperature remains the same while the phase change is occurring until you turn nothing but a gas, and then the temperature can increase again. And really, you can do different equations. When, like from A to B, that's going to be the equation Q equals MC delta T, because the temperature is changing. From B to C, that's going to be Q equals N delta H, because that's the phase change. So you might get what we're going to be doing here, calculations with this. Now let's say I'm a cooling curve, which would just be going this way. The same thing happens for if you start at F, you have nothing but a gas and it starts to cool until you get to point E. That would be the condensation point. It's the point in which it starts to condense. And then you have a gas and a liquid as the phase change is occurring, and then the temperature can decrease until it's a liquid. Then you get right here, and that's going to be the freezing point. In case you didn't believe me before that they occur at the same temperature, if the melting point's here and the freezing point's here, that's at the same temperature. Boiling point, condensation point, that's the same temperature. Again, it just has to deal with, is the energy going in or is it coming out? Super important concept. So finally, let's do some calculations with this heating curve. That's the last thing that we're going to, no, we're going to do the thermodynamic equations too. But let's do this calculation for a heating curve. How much heat in kilojoules are required to heat, well, there's a little typo here, 15 degrees Celsius, that would be water, to steam at 127 degrees Celsius. And you see here, we have different specific heats for ice and steam than we do for water, okay? Different states of matter have different specific heat capacities. So what we need to do is a couple things. The first thing that I would have to do is go from 15 degrees Celsius to 100 degrees Celsius. That's my first step, okay? And that would be the equation Q equals mc delta T. My second step is going to be doing the phase change. Okay, we're going to go from a liquid to a gas, and that's going to be Q equals N delta H. And then finally, for the third step, I'm going to be doing from 100 to 127 degrees Celsius using Q equals mc delta T. Those are the three steps that I need to do. And then my answer is just going to be all three of those things added up. Okay. So it's like we're following along on this heating curve. We are here, let's say here. We have to go here, then here, then here. So we have the three different unique steps that we need to do. Okay, so I have to erase this just because I need room. So pause if you need to write those three steps down, because then I'm going to do them now. Now, it's important to note we need a mass. Let's do 100.0 grams of water. I just left that part out. So the first step we were going to do is the Q equals mc delta T. So the mass is 100.0 grams times the 4.184 because we're water, times the change in temperature. We're going from 100. No, we're going from 15 to 100. So that's going to be, we'll take 100 minus 15. And that Q will give me, with the correct number of sig figs, 36,000 joules, which I'm just going to convert into kilojoules. That's going to be more useful to us. Second step is the phase change. 100 grams of water, when you convert that into moles, we did this previously, it was, what was it? 5.556 moles. Okay. So we're going to do Q equals N delta H, and this is vaporization. So it's going to be equal to 5.556 moles times the 40.6 kilojoules per mole. And that Q will give me 225.6 kilojoules. So we've got this Q, we've got this Q, and then the third one we're going to do from the 100 to 127 degrees Celsius. So we're going to again do Q equals mc delta T. So that's going to be 100.0 times, now we have to use the C for steam, 2.03 joules over grams degrees Celsius times 127 minus 100. And that Q will equal 5,500 joules, which is 5.5 kilojoules. So now, for my final answer, we just add them up. So the Q total will be equal to 36 plus 225.6 plus 5.5, which gives me 267 kilojoules. So it takes 267 kilojoules of energy in order to go from 15 degrees Celsius as water to 127 degrees Celsius as steam. It's important to note that phase change was where most of our energy went. Okay, changing the state is going to take much more energy than it does to increase the temperature because we're breaking those intermolecular forces. Okay. And then the final thing for today is looking at a thermochemical equation. We've seen these previously when we were doing stoichiometry. Thermochemical equations are chemical equations that include heat as either a reactant or a product, which we've seen. For example, you take methane, reacts with oxygen, it produces carbon dioxide, 2 moles of water, and 427 kilojoules of energy. So we can use energy diagrams, which are also known as enthalpy diagrams, to show a visual representation of what's happening in a reaction. So on the y-axis, it's energy. On the bottom, it's time, or you can see it as reaction progress. So I'm going to show you one for an exothermic reaction and an endothermic reaction. So my reactants are up here, my products are down here. You can see from where the reactants are to where the products are, my delta H, my enthalpy is negative because I start higher and I go lower with my energy. This is exothermic. That's what an exothermic reaction looks like in an energy diagram. Reactants are higher, I lose that energy, my products are lower. So an endothermic one, my reactants are down here and my products are up here. And so you can see my delta H is positive. And that's going to be an endothermic reaction. Now that hump right here, this little area right here, that's known as my activation energy. We're going to talk more about this when we talk about kinetics, but the activation energy is the energy that's needed in order for the reaction to occur. So you can see the activation energy on both of them is that little hump. It's basically the hump you have to get over in order for the reaction to occur because all bonds need to be broken, rearranged, and then form new bonds. We will talk more about the activation energy later. I just wanted you to show you the difference between an exothermic and an endothermic enthalpy diagram or energy diagram. And that's it for this module's lesson. So again, the main takeaways: Q equals MC delta T, Q equals N delta H. Those are the two big equations that we looked at today. And doing those calculations on the heating curve that incorporate both those equations, super important. Of course, if you have any questions, please feel free to ask them, put them in the chat, ask them at the end of class, and I will see you later.